Okay, so now I want to talk about this theorem. It's quite important. It's called the rank nullity theorem. Given a linear map between two spaces of finite dimensions E and F, we have that the dimension of the domain E is equal to the dimension of the kernel of F and the dimension of the image of F. Why is it called the rank nullity theorem? Just simply because that's the definition of the rank of F. And remember that what we call the kernel is just a general term for any linear map of what you used to call the null space of F. Okay, and so the nullity is just going to be the dimension of the null space of F. Okay, and so the sum of those two dimensions gives you the dimension of the domain. Okay, so why is that true? All right, let's assume that let's give some name to these dimensions. Let's say that dimension of E is equal to n. And so the kernel of F is a subspace of E. You remember this is one of the fundamental spaces. So it's a subspace of the domain, and we know that the dimension of the kernel of F is smaller or equal to n, and so we can say that it is spanned by let's say that the dimension of the kernel of F is equal to P. It is spanned by some P vectors. Let's call them E1 up to EP. Okay. One of the theorems that you should remember from, I think it was in the first lesson that we saw, it's called the incomplete basis theorem. So this theorem tells you something that is actually very intuitive. It tells you that if you're in a finite dimensional space of size n, and you already have p vectors, then you can complete this basis with as many vectors as you need in order to span what you need. So we can say that we can find vectors EP plus 1 up to En, as many vectors as we need. So we have n minus p vectors, such that the whole system from E1 up to En is a basis of E. Okay, I've got n linear independent vectors in a space of dimension n, so I know I can make a basis. Okay, so let's see what we can do with this. Then, as you know, the image of F is just going to be spanned by the image of vectors of a basis. Okay, so F of EP plus 1 up to F of En. Okay, the fact that I have my basis in two parts is quite so I've got one part from E1 to EP and one second part from EP plus 1 to En. Yeah, well, it doesn't change the fact that the image is going to be spanned by this system. So what do we have? The thing is that all these are equal to 0 because they belong as E1 up to EP, they belong to the kernel of F. They span this kernel, so they also belong to it. So it means that their image is equal to 0. Okay, so the image of F, well, all these vectors, it doesn't bring you any information. It's just 0. So first of all, it makes that your whole system here is not linearly independent. Now, if I want to find the rank of F in order to extract the rank to if I want to know the number of linearly independent vectors, I must I must forget about my E1 up to EP because they all make 0. So, and then you wouldn't have a linearly independent vector. All right. So, but the idea is that the span doesn't change if I just forget about those vectors. So the image of F is also spanned by F of EP plus 1 up to En. Okay. The thing is that are they linearly independent? Well,